Hello everyone, this is Yura Samoshka. Let's wait a couple of more minutes and see if anybody else joins us. If not, we'll start at 13:04 in our time. Okay, so I guess that's everybody. So once again, my name is Yura Samoshka. I am one of the project managers here at Energy Advice, responsible for part of the digital twin implementations in the biomass power plants. And so we'll start with the webinar on optimizing biomass power plants using digital twin technology. So the webinar will be split into two parts. 30 minutes, roughly 30 minutes for the presentation part, and then the 30 minutes for the discussion part. So if you have any kinds of questions during the presentation, so that you don't forget them, leave them in the chat and we'll open it together during, well, the Q&A session, and we'll unmute ourselves and talk about it or just talk through chat. So the topics will start off easy. So first of all, what is digital twin? Then we'll go over what is like the differences between digital twin and traditional control systems. Then move over to individual test cases or use cases of digital twin, and wrap everything up using real project result overview. So what is a digital twin? Simply, it's a model of a physical process. In our case, it's the process of biomass burning. So you have real-time data, for example, the temperatures in the furnace, steam flow, fan frequency converter data, everything, in other words, everything that you can see in the control system. And you also have then the technical data. So what you got from the commissioning engineers, like a big book or a big PDF with all of the information, the technical paths, the diagrams, the fan characteristics. Once you have these two groups together, you join them and you have the digital twin of your process. So this has only recently become, like, it's becoming more and more widespread because each year more and more data is readily available, and data collection has become more and more standardized. So for example, if you collect the data from one biomass power plant, it's going to be probably the same kind of process in another biomass power plant. So you have one model of the biomass power plant already done. It's going to be similar in another biomass power plant. So you save the time and you already have the knowledge about the project. So why would you actually use a digital twin in your power plant? Well, the power plants have fluctuating processes. So for fluctuating operating modes, fuel quality changes, moisture content isn't stable, or demand for steam just drops. So while you can manually calibrate for one of those kinds of process operating modes, so for example, at peak demand, once you move over from it, like once an hour, twice an hour, your efficiency just goes down. So this is where digital twin comes in. In our case, we described a biomass power plant using 150 equations. So it's like a whole mass energy balance. So, and including each component, the economizer, condensing economizer, furnace, boiler, everything about the biomass power plant is well written in math using those 150 equations. And these kinds of calculations are just too much for a single person to well do in 1 hour time, 2 hours time, but digital twin works 24/7 with this. So each 5 minutes, the state is calculated. Then the calculations are used to predict the next 5 minutes. And the final task is to optimize how the digital twin can move the set points at least a little bit in order to optimize the process and get the higher efficiency. So in essence, digital twin is calculation, prediction, and optimization. I myself like to think of it as a second brain for your power plant. Yeah, you have the control system and it makes the plant work good enough and not burn up. But digital twin takes it to a new level by controlling the set points instead of the operators. So the set points are no longer influenced by human factors like experience, knowledge. Of course, the digital twin works within the zones that are set by the commissioning engineers, but it's still much more quickly changed than by hand of the operators. Okay, so I am mentioning traditional systems and digital twins. So what's the difference? That's actually the number one thing that I get asked when I'm describing digital twin. So because the number one answer is, I already have a control system, everything is automated, and nobody has to do much of anything actually. Yeah, all of the power plants are running control systems using PLCs. The PLCs don't have, well, they perform just basic math. They have to do the calculations in a reliable way and draw as the minimum amount of power required to do the calculations. The calculations are also done in PID mode. So, and the task is given by the operators. So once again, the operators are giving the PLCs set points to operate. So this level of control is fine for linear processes. For example, stopping an elevator. You don't want the elevator to come to the second level and abruptly stop. You want it to come fast, start slowing down, and then gently stop. So the PLCs are fine for that, that's okay. But biomass burning is not a linear process. So much more sophisticated math is needed in order to find the optimal solution. This is why digital twin takes much more data than single PLCs do. So what changes from your perspective is that the operators only monitor the digital twin. The digital twin becomes responsible for controlling the PLCs, and the PLCs control the pumps, the valves, whatever parts of the biomass power plant that are needed. So in the short term, this means the digital twin makes recommendations for the set points. It's like an advisor for day-to-day operations. In the long term, it's possible to find the limitations of the operating zones. So you can bring in the commissioning engineers to adjust them. And once you have more room to work with, because of course they set safety margins that are quite bigger than they are needed to be. So then you have more ways to optimize the power plant. So digital twin expands its capabilities, it enhances the power plant, and long term, it is an enhancer for the biomass power plant. So that's the simple theory behind digital twin. Now the question is, how would you integrate it into your power plant? So the first thing is, I'd like to emphasize that digital twin control doesn't mean that you throw out your control system. It means that digital twin works together with the control system that you have in place in order to find, well, the optimum operating mode of your power plant. It is also modular by design, meaning that you can use the different kinds of modules in a plug-and-play manner. Analysts don't actually need any kind of well, automation or programming skills in order to take advantage of that, add or remove calculations, or add additional measurement devices. For example, if you want to add a new electrical measurement device for the pump, you physically connected all the wires and you have an IP address for it. And then you have the documentation once you buy the measurement device, and you go to the digital twin, push a button to add the measurement device, specify the IP address where to look for it. Then you say that it's, for example, active power, and then that it's in block 3 using Modbus protocol. For example, all of that information would be in the documentation side. And then you have the data collected in real time. Question is, how do you want to use it? Will you use it in your calculations, or do you want to have a report, for example, that the pump has been using for the past week this much of electricity? Just as an example. So no automation or programming skills is needed for that. You just pick what measurement device you want and what kind of information to collect from it. That's it. Now, if we're talking about the whole digital twin for the biomass power plant, well, in 99% of the cases, we didn't find that any additional devices, measurement devices, sensors would be needed, and that the automation level is adequate. Well, there's a disclaimer that most of our biomass projects are in 5 megawatt and up, 5 megawatt thermal capacity and up. In those cases, yeah, we find that 99% of the cases, it's okay. So why the automation level being high enough is important is that data collection is not such an issue. That, as I said, that this data collection is becoming more standard. So you can easily plug in, for example, in our case, we have our own software that is dedicated for gathering the data, and it works with all of the standard protocols in order to collect the data. And then, well, you have the control system in your hands, all the data, the technical data from you, and you can integrate the digital twin. In other words, no hardware changes are needed from your side. It's software only. And it is also running in the cloud, so you can access it through anywhere. You can access it, for example, let's say you're working from home, you can do it, but you program, well, you give permissions that your operators cannot access it from anywhere and change the settings, just as an example. This slide is a document that we have prepared about what kind of measurements are needed. We'll skip over it for now, but if you'd like to get it in the email, you let me know, or we can just talk about it during the Q&A session. This is all the measurements that are needed for the digital twin. Okay, so now we go in more detail about the digital twin. So first, I'd like to note that all of the calculations are done in real time. We use reverse engineering in order to calculate the amount of, for example, burned fuel, the calorific value of the fuel. In other words, we use the output of the power plant in order to understand the input. You have the digital twin is like a black box where the algorithm is running and it interprets from the output into the input. So once you have the input and output, you can understand, and then you divide them. So for example, the megawatts that you have produced and the megawatts of fuel that was being burned. So now you have the efficiency of the biomass power plant, and you can see it, and the digital twin is responsible for making it work at a higher efficiency point. On a smaller scale, each component is also calculated. So for example, the heat exchanger efficiency module part is that you input data about the direction. So for example, this is data from the technical past that says that the direction is like that, and that the P thermal, so like how much heat you're inputting into the heat exchanger, that is already real-time data. And you input this into the heat exchanger black box, let's say, and then you get the output about the heat transfer coefficient. So in our case, we use this and our clients use this to understand, should the heat exchanger be well cleaned right now? Should we stop it? Which, for example, heat exchanger should be cleaned, which can be be left for now, and etc. So these are different kind of modules in digital twin. So moving on, there is also the capability of, well, if we have the fuel specifics of, using reverse engineering, so we can also handle the unstable fuel and increase its efficiency. So the burning process has inertia. So if you change the fuel, the amount of fuel, the control in the biomass boiler, it won't affect anything at the same moment. So digital twin calculates fuel in 5-minute intervals for the next 5 minutes. It's like educated guesses are made to estimate what will happen in the next 5 minutes. These guesses are used to optimize the grate movement, air supply, recirculation, what is chosen to control. In our case, what we do is we act as a doctor. So we see that, for example, okay, air supply, or one of the fans has this kind of effect on the efficiency. Okay, that is good. Another zone doesn't have any kind of effect, etc. And then we find that what is the most useful to use, and then the control starts from there. And then you see that the efficiency goes up. And again, after the 5 minutes of using the control, the digital twin cross-checks it automatically in order to see what kind of effect there was. And then the cycle happens again. Calculates for the 5 minutes, predicts what happens, optimizes. Again, the essence of digital twin. So this is how the changes in fuel quality and consistent fuel is being fixed using digital twin. Another module for bigger power plants is aimed at decreasing NOx emissions. So they're a natural part of the burning process. You just can't, it's impossible to remove them. But by injecting ammonia water into the flue gas at the right temperature, it's possible to mostly neutralize the NOx. The problem with that is that the neutralization process is most effective between 850 Celsius and 1030 Celsius. So now the task is to find the optimal zone for injecting the ammonia water. But the problem is that flue gas temperature fluctuates based on for example, the height of the flame. If the demand is high, the flame will be at a higher point. If it changes rapidly and then drops down, okay, so you have to go to zone 2, maybe a lower zone. Just as an example. So digital twin calculates different kind of, in the zones, the different temperatures, and then finds the correct one that is most near to the optimal temperature of between 850 and 1030 in order to inject the ammonia water and reduce the emissions of the biomass power plant. Another module is the cross-checking of measurement device accuracy. So as we already established, the digital twin has the whole mass energy balance already calculated. So in the simplest example of detecting faulty measurement devices would be flue gas temperatures. In this case, I can show it. The client had four flue gas sensors installed, but there were some kind of discrepancies between these sensors, and they suspected that one of them might be wrong. So in this case, based on the theoretical estimated temperature here, it was found that actually 3 sensors were bad, and only one of them was, well, within spec in to show that the correct temperature. So this is how digital, and then you can set up like automatic notifications. So for example, if you have a graph here with the estimated temperatures and the real, well, the measurement device temperatures that it reads, then you can set up notifications, for example, that it's more than 10% error. So this, and then you get the notifications in order to check it out. The most common problem is that it's the flue gas temperature sensors are just, well, they're covered in ash. So then you just know which sensor you need to, well, to clean off, and then you have, well, again, functioning temperature sensors. So that was pretty much the overview of digital twin. And I'd like to move over to the real project results, but before that, a common problem with digitalization projects, and as we talk with clients that are, well, at the early stage of digitalization, or at least have the first steps of it done, is that, for example, monitoring solutions don't have any way to calculate the return of investment. So you have all of this data that you collected, you spent a lot of finances in order to get the measurement devices up and running, and now what do you do with it? Some clients just stop at the point of just looking at it. But how we approach this problem is that we calculate the digital twin return, well, the savings based on the fuel saved. All of that other functionality, like the maintenance parts, is just extra value for you. So with that out of the mind, let's move over to some of the case studies that we have. The first one would be a heating utility with a moving rate power plant. So take note that it's a 3 megawatt power plant. So as I said, we mostly work with 5 megawatts and up, but this was a newer power plant from 2019. So it had the capability to output the data. The problem is the automation part. The first problem, well, in most cases, it's too high of a biomass consumption. So they want to fix that. But one of the causes we found for that is that the operators weren't able to control the power plant with the automation that has been, well, put in place for them. So for example, you need to have a higher, well, you need to produce more heat, so you put in more fuel. And then the fuel starts burning. And then they were unable to stop the process, and the temperature got too high in the furnace and it automatically stopped. So, okay, so the temperature goes up and then it crashes down, and then you need to put in more fuel, you need to put in more air, you need to, well, play with the control system in order to stabilize the process. So it's a good thing if, okay, once you crash, you get back. But what happens if it's 2-3 times? You waste a lot of fuel, and the stability of the process, well, there is no stability in that. So what we did is we started as an advisor in their case in order to find the correct amount of fuel that should be brought into the power plant. What is the correct amount of primary air? What should be, which zones should the primary air come in through, the recirculation values. And then through trial and error, we saw that the automatic stops just stopped happening because this, well, it became more stable. And during, well, we calculated this for 6-month period. It was 3% reduction of, well, biomass consumption. So, and of course, there are also other kinds of values. So one funny thing is that the operators actually forgot how to operate their power plant. So one time they had maintenance and they didn't have like the internet in their case, so they couldn't see like what task should be given to the power plant. And then they had to call us in order to find out what should they do, even if they worked with those power plants for like a couple of years, 3 years already, and they had forgotten it over like a 6-month period. So what I wanted to say is that we also installed automatic control in this power plant, and they just forgot how to do their jobs. And another test case study is another heating utility, this time a 5 megawatt one. With them, we already have near to close 1 year of automatic control from the boiler side and the district heating supply. So we have the full power plant and network inside of, well, as a digital twin. So before the project started, the main problem that they had is inconsistent fuel consumption over the months. Operator inexperience was the main suspect, and so digital twin was like a no-brainer, and we actually moved quite quickly to automated control also. In their case, they were able to increase their efficiency by even 10%. So to date, this is the best project in terms of biomass saved that we have. Of course, this is combined by the district heating side and the boiler control side. Also, in this case, it's also worthy to notice, I mentioned that digital twin in the long term is an enhancer of the power plant. In their case, by using digital twin, it was possible to see that the PLCs were seesawing. So they were coming up rapidly and then dropping, like from the automation part, and you could see this over different kind of measurement values, and you could see when they would, and you could predict when they would start to drop actually. So this is when we advised, based on the evidence from the digital twin, to bring in the commissioning engineers to redo the automation part for those kinds of sensors on the PLCs, in order to increase the efficiency and stabilize the process. So once again, before digital twin, they didn't even know that they had a problem like that. But by collecting more data and analyzing it in real time, it was possible to find the limitations of the currently installed system. And now moving over to a different profile of a client. So this was, a company using an 18 megawatt biomass boiler in steam production. It is a pulp and paper company. So before, once again, the main problem was high biomass consumption. And then there was like the lack of experienced operators. Actually, here in Lithuania, we hear that from a lot of the district heating companies that there are less and less experienced operators available that would actually want to work at the power operating room and manage the power plant. So this was another way for them to increase the amount of people that could work on their power plant. And of course, the company wanted to reach their CO2 emission goals. So once we started the project, we saw that the steam production wasn't stable. So that's the number one thing that should have been corrected. We saw the information about the flue gas temperature sensors. That was also done for them in order to find which one was the correct and good sensor. And they're also using the digital twin in order to find, make their maintenance decisions based not on human experience and just guessing or planning when to actually perform the maintenance, but on data-driven decisions. So the digital twin can see, for example, if we talked about the heat exchanger efficiency, so you can start to see that it goes down, and then you say that at this efficiency, we should clean it, maintain it, do whatever with it. And this is how they base their maintenance decision. And of course, the main thing is, once again, reducing the biomass consumption. In their case, it was almost 3%, so 2,700 megawatt hours in the first year of operation. In their case, I'd also like to expand on their case is that they also have another power plant, a 10 megawatt power plant, and we're also well, we have installed the digital twin in it, but we are also doing automated, well, experimenting and doing automated control with the second power plant. And in the near future, it's planned to have like the whole production of the steam side and also the consumption of the steam side in one system. So the digital twin would see all of the production, well, the production and the consumption sides, and then it could be all used to automate the processes instead of the power plant personnel seeing that the demand for steam has dropped significantly, and they need to quickly react to, well, the changes in the demand. And we already said that the biomass burning process has inertia. So now they have a hard time, the efficiency is lower, they burn more fuel, etc., because the two sides aren't talking to each other. But as I said, it's planned to have both of the sides together. Okay, so this was actually it for like the presentation part. I believe we took like